So, good morning, everyone. Thanks for joining our first webinar on the grid forming battery series. So, this is Insights webinar is going to cover the first report of the grid forming battery portfolio series, which we call the summary report. I want to start my slides. I'm not moving. Here we go. Yeah, I want to start by acknowledging the traditional custodians of the country across lands we all meet today and pay my respects to elders past and present. I am Tanya. I'm in the large-scale integration team here at ARENA, and I lead the knowledge sharing coming out of the projects in this portfolio. The large-scale integration portfolio sits under the ARENA's strategic priority of optimizing the transition to renewable electricity and has as one of its goals to ensure system security in 100% renewables grid. And supporting the advancement of grid-forming battery technology is crucial to achieve this goal. ARENA-funded portfolio of grid-forming batteries has 6 projects operational with grid-forming capability enabled, and another 5 projects I expect to be grid-forming enabled by 2026. This summary report, which is the first report of the grid forming battery series and the subject of this webinar, covers the insights from 4 of these projects: the Walgrove battery, the Hornsdale battery, the Darlington Point battery, and the Broken Hill battery. The second report of this grid forming battery series is the update report and is expected to be published sometime in August. And will cover insights from the projects from the 2022 round. And both reports were commissioned by ARENA to Ekistica, which is also presenting this webinar today. And let's now move to the webinar. I'll pass over to the presenters, Josiah and Caitlin, very soon. But before I do, just a note that we are going to use the Q&A box in Teams for questions. So feel free to pop in questions at any time during the presentation, and they'll be addressed at the end of the presentation during our Q&A session. And now I'll pass over to you, Josiah and Caitlin.
Tanya, I'm just sharing my slides now. Are those coming through? Yeah, perfect. All right, thanks, Tanya. So just by brief introduction, Ekistica is an advisory and technical consultancy firm with expertise in energy, water, and remote infrastructure. My name's Josiah. I'm the practice lead for infrastructure analytics, and my colleague Caitlin, who's our energy advisory practice lead, will be presenting today. And my colleagues Lyndon, Paul, and Ash are also online for the Q&A as well. So this presentation will go through the summary report. And it'll follow broadly the structure of the report itself, as you can see up there. And I'll start with a brief background, some of which Tanya's already provided. And to begin, as Tanya mentioned, these are the 4 projects that were the subject of this report. They underwent the grid connection and commissioning processes over the period from around 2020 through to 2024. And we now have several years of operational data, particularly from the Hornsdale and Walgrove BESS, but also from the other projects as well. And so this report really draws out some of the findings that have been found through those operational periods and the subsequent knowledge sharing. So to provide a bit of context for what these projects were attempting to achieve and the purpose for the projects, it's well recognised that as the larger thermal generators are retiring and there's a rapid growth in wind and solar resources, inverter-based resources generally, there is a growing need for new sources of system stability on the network, particularly inertia and system strength. And the purpose of these projects really is to demonstrate that grid-forming batteries can provide that capability and show them providing that capability in real-world conditions. So this is part of an ongoing body of work from AEMO, led by AEMO, to validate and define the way that grid-forming technologies can provide these services. But one thing we highlight in the report is the significant shift that we've seen in the acceptance that grid forming batteries can provide these services across the industry in Australia. And it's worth calling out in 2019, at the end of the large-scale battery funding round, the initial first 5 large-scale batteries in Australia, there was a knowledge sharing report summarising the findings from those projects. And in that report, commissioned by ARENA, it noted that while grid forming batteries could provide inertia and system strength capability, there was uncertainty around how well this could be provided, and there needed to be more demonstration of this capability. By contrast, by 2024, we saw Transgrid's RIT-T process explicitly acknowledging that provision of efficient levels of system strength by grid forming batteries would be part of the optimal solution in New South Wales, and similar statements followed from the TNSPs in Queensland, SA and Victoria. And at the same time, AEMO also published a methodology for how grid forming, the contribution to inertia network services from grid forming batteries could be recognised. So it's really quite a shift that's occurred over the past 5 years. And along the right-hand side of the slide there, you can see some of the key milestones in that process, including some key reports by AEMO and the publication of the voluntary specifications for grid forming inverters. But what's worth noting is that these 4 projects and the knowledge sharing associated with them have been one of the key drivers for this progress. And that's one of the things we've tried to highlight in this report. So before getting too deep into the technical details, I'll just give a very brief overview of some of the key terms that we'll be talking about. The first one, of course, being what a grid forming inverter is. So it is an inverter. The key defining feature is that it has an internal voltage source, and it's not dependent on the external grid for a voltage and frequency reference. And what this means is that it inherently can resist changes in the voltage and the voltage phase angle on the grid, and have an instantaneous active and reactive power response to disturbances. And so that's obviously in contrast to grid following inverters, which do require that grid reference. In terms of inertia, we use the term synthetic or virtual inertia to describe the inertial response that's provided by grid forming batteries. What's important about this is that it's an inherent transient response. So it's based on the difference in the voltage phase angle between that internal voltage source and the voltage source at the point of connection. And there's a control architecture that surrounds that response and is designed to mimic the response of synchronous machines. But the actual inertial response itself is inherent to the technology. It's not a measurement of a frequency deviation and a response to that, like very fast FCAS that can be provided by grid following inverters. It's an inherent response to the change in frequency, to the rate of change of frequency. And lastly, the term system strength, as we're talking about here, we're generally talking about contribution to a stable voltage waveform. That is the type of system strength support that the projects we're discussing today are providing. And we're also talking about the fact that these batteries can operate in very low system strength areas of the network, which is something that grid following inverters aren't able to do. And just worth flagging that last dot point there is that this particular paper and these particular projects sit within a broader process that's happening not just in Australia but also internationally to standardise and define across different manufacturers what we mean by grid forming technology and what the key services are. So it's not actually completely agreed at this point, but there is growing agreement and alignment across all those different international bodies and the definitions that AEMO has published as well. So just a brief overview of the approach to the paper. We reviewed the 26 knowledge sharing reports that were published by the projects at the time. And I will stress again that it's a summary report. So we couldn't obviously cover everything, and would definitely encourage people to go and have a look at the actual reports and see some of the findings there firsthand. But we also had a roundtable in December 2024 discussing with the 4 proponents the technical performance and grid connection process. And we followed that up with one-on-one interviews with the proponents to further draw out the themes. And as Tanya flagged, there's an update report that will be coming out shortly, and that will cover the next round of projects. So with that background done, I'll dive into the first key theme that emerged from the paper, which surrounds the grid connection process. So the key finding that emerged from all the projects was that there was a mismatch at the time when these projects started the grid connection process between the generator performance standards and the access requirements in the standards and the type of response that grid forming batteries were designed to provide. So under the national electricity rules, there are different access requirements based on the technology type, which is broken down into synchronous, being thermal generators, traditional rotating machines, or asynchronous, which are inverter-based resources. However, there isn't a further distinction between within inverter-based resources, but within asynchronous machines, between grid forming and grid following responses. What this means is that the grid forming inverters were being held to standards and required to meet the access standards that were originally developed for grid following inverters. And that presents challenges because as we described earlier in the actual definitions of the way these machines respond, so this equipment responds, it's actually trying to provide a response that is more similar to synchronous machines. The key clause that arose across all the projects presenting challenges was 5255, and within that particularly the reactive current rise and settling times. And I'll talk a bit more on that in the next slide. And there were also some challenges observed in the 539 process for projects that were transitioning from grid following to grid forming modes of operation. There have, however, been a series of rule changes that have occurred throughout the life of these projects, and we'll go into those in a bit more detail as well. So just to provide an illustration of the trade-off that occurs, the challenge is that grid following inverters directly control the current, and the response within the standards is typically that they need to return very quickly post disturbance back to the original level of operation prior to the disturbance. And the grid forming inverters, by contrast, are designed to actually respond to the disturbance and try and reduce the disturbance. So this graph here is from Hornsdale Power Reserve, and it's showing the active power response of Hornsdale Power Reserve to a disturbance. And the different lines show different levels of inertia that the battery has been tuned to provide. So the red line you can see is when there's a high amount of inertia, a high inertial constant that's been tuned. And so there's a larger response to the disturbance from the battery, and it's faster acting as well. However, it takes a longer time for the recovery period to return to the pre-disturbance levels. Whereas as you reduce the inertial constant, these other lines there, and the blue line actually shows the equivalent of a grid following response, there's a smaller response to the disturbance, but you have a faster recovery time. So that's for active power, but a similar general trade-off is observed for the reactive current as well. Essentially, if you are harnessing more of the fast-acting response of the grid-forming technology to the disturbance, you have a longer settling time, and you struggle to meet the settling time and reactive current rise time requirements within the standards. This was explicitly noted by Walgrove and Darlington Point that the amount of inertia that the grid-forming battery could provide was limited by the need to comply with 5255 of the performance of the access standards. And similarly, Hornsdale did actually have capability to provide up to 3,000 megawatt seconds of inertia or the equivalent thereof. But because primarily due to 5255 and other considerations around the stability of the Hayward interconnector, the inertial response was limited to around 2,000 megawatt seconds. So there's a trade-off there under the current rules between the full utilization of the grid forming capability and the need to meet the standards that were actually designed for grid following inverters. The other before I move on, there was one other point I wanted to flag. There was a really interesting example on this trade-off that was also noted by one of the projects, which was a different project, not within the portfolio, where there was one of the access standard requirements was the response of the inverter in a very high rate of change of frequency scenario. And because of that particular scenario that was being modeled and compliance was required within, the inertia that the BESS could provide had to be reduced. But there was a bit of an irony in that particular example, because the more inertia from the BESS would actually make the future scenario where there's a high rock-off less likely. But it's sort of a counterproductive requirement where you're making the high rock-off scenario more likely by limiting the inertia that the BESS can provide. I thought that was an interesting example that we came across. So the other key finding that was observed, particularly at Hornsdale and Wargrove, was the transition from grid following operation to grid forming operation. In theory, this is actually quite a cost-effective change to make. It's a firmware update to the technology, and there's no inherent requirement for additional hardware to make this change, depending on the particular manufacturer. However, there were challenges in the way that the 539 process operates when this change occurs. In particular, the challenge that existed at the time was a clause in the NER that required the new standards applicable to the new mode of operation to be no less onerous than those that applied when the BESS was operating in grid following mode. And so this meant that not only were there the sort of mismatch that we'd observed previously between the standards that applied to grid following inverters versus grid forming, you also had just the more stringent standards that applied when the BESS originally connected, or the standards that the BESS agreed to meet in grid following operation still applying to the BESS when it had transitioned to grid forming operation. So this was ultimately resolved for both projects, and there was some negotiation with the TNSPs and AEMO around the acceptance that the BESS was actually helping the grid as a whole. And it's also notable that specific clause has been removed now, and there's no longer a requirement for the new standards after a 539 to be no less onerous than those at the time of the original connection. And one last thing to note on this transition, the approach of connecting in grid following mode first and then subsequently doing a 539 process to transition to grid forming was explicitly adopted by Hornsdale and Wargrove to mitigate the risks that were seen at the time and the uncertainty in how long it would take to complete the connection process for grid forming mode. And while some of that risk still does remain, and which we'll discuss a bit more in the forthcoming paper, there is definitely signs that, especially for projects where the grid forming inverter has already achieved grid connection elsewhere on the network, there is less of a need to start in grid following mode first and then subsequently transition to grid forming mode. And so more projects are directly going through the grid connection process in grid forming mode, which is what we saw at Darlington Point and Broken Hill. So the summary of some of the key reforms that occurred in the later years of the project's connection and operations. What we're pointing out here is that, at least in part, some of these changes actually came about because of the challenges that were highlighted through these projects. So the first one being the removal of reactive current settling time from the minimum access standards, which occurred in 2023. The Broken Hill BESS, one of the Broken Hill BESS reports explicitly notes that the removal of this requirement would have actually made connection easier for the Broken Hill BESS if it had applied at the time. And then the next change was the one mentioned previously, is that the removal of the no less onerous requirement when undergoing the 539 process, and now the new negotiated standards for projects in that position is the lesser of the current standards or those that applied originally to the project. And the big one was just in May this year, the improving the NEM access standards package of reforms. And what's notable here is that that rule change, within the rule change, it was explicitly noted that some of the existing access standards aren't fit for purpose and actually disincentivize grid forming operation. And there have been changes within that rule change, including the complete removal of reactive current settling times from the GPS, which will, based on what the examples we saw in this set of projects, that should improve the process for grid forming technologies. The full implications remain to be tested, and we have a further discussion of that particular package of rule changes in the forthcoming report. So last point on grid connection was some of the strategies that were employed by the projects to overcome some of these difficulties that were present at the time when the connection process was occurring. The main finding really was a need for very close collaboration and communication between the project proponent, the original equipment manufacturer, AEMO, and NSPs, and regular meetings, quick feedback around issues that arose during the modelling process to ensure that the information was getting through right from the inverter manufacturer through to the NSP. And also, there was noted from the Wargrove BESS that there was a great degree of flexibility that was needed on the part of the NSP and AEMO and all parties to achieve the connection. The hope is that this need for sort of flexibility and cooperation will reduce over time as the improvements are made to the access standards. But in general, that general collaborative approach is certainly a way of mitigating the risks that still exist associated with that mismatch discussed previously. The other keynote was the use of different simulation and more advanced simulation technologies, including hardware-in-the-loop testing and real-time digital simulation. That was particularly highlighted by the Broken Hill BESS project, and that was particularly flagged as something that could improve the predictability of the grid forming response in weak grid conditions. Hornsdale as well had a period of hardware-in-the-loop testing that was used at the very early stages of the project to demonstrate to AEMO the response that would be provided from the grid forming capability and build confidence in the response. So turning now to synthetic inertia and the findings related to that particular capability. Synthetic inertia was the particular focus of the Hornsdale and Wargrove projects. And the overarching finding is that we now have several documented examples that and really great detail on those examples where these grid forming batteries were observed actually providing an inertial response to disturbances on the network, which is really positive to see. And on the right here is one example from Hornsdale that illustrates the distinction of the inertial response from just the typical response that would be expected from a grid following battery. So I'll just go through this briefly. At the top here, you can see the grid frequency. So the particular event that we're seeing here is a large drop in frequency that occurred. And at the bottom, the bottom graph, that essentially shows what response you would expect from a typical grid following battery that had fast FCAS response implemented. And so you can see that the peak of the response from this bottom graph occurs at the same time as the peak in the frequency deviation. So that's, as would be expected, the sort of primary frequency response of the battery is proportional to the magnitude of the frequency deviation. But this second from the bottom graph is where the inertial response can be observed. And so you can see that the peak of that response is not in line with the peak of the frequency deviation, but rather the steepest part of the frequency curve. So it's proportional to the rate of change of frequency. And that is, of course, how the inertial response is designed to be. It's proportional to the rate of change of frequency rather than the frequency, and that way it provides a faster response to grid disturbances. And so then you can see in the second from the top graph, the combined response of the battery. So that is that particular example. As I said, there's many examples throughout the knowledge sharing papers, and would encourage people to go and have a look through it and see how these operate in practice. One additional finding, though, was getting into more detail. The focus of the Wargrove project, one of the focuses of the Wargrove project, was to actually compare the inertial response of the grid-forming battery to the inertial response of synchronous machines. And so, yeah, again, would encourage you to read the flagship report from Wargrove, which goes through many different pieces of analysis in detail on this particular point. But one particular example that we're highlighting here is a frequency drop when the Kogan Creek generator tripped. And what you can see on the graph is, in blue, the response of a nearby synchronous generator on the New South Wales grid, and in orange, the response of the Wargrove BESS to the same event. And what was highlighted in the report was that the peak of the inertial response for the synchronous machine occurred slightly earlier than the peak of the response from Wargrove, which occurred about 480 milliseconds later. And then you can see that the larger response from the battery occurred after that point, which is not the inertial response. That's the primacy frequency control response, the standard sort of FCAS type response from the battery. So the initial conclusion was that there is just a difference in the nature of the inertia that's provided by grid forming batteries. It's not a like for like replacement for synchronous machines. However, there is a heavy caveat on this particular graph. This is just one example. The main one being that it's very, very dependent on the way that the BESS is tuned. So unlike synchronous machines, where the inertia that's provided is just an inherent electromechanical property of the machines, for grid forming batteries, the magnitude of the inertial response can actually be tuned, and also other aspects of the response can be tuned as well in terms of the damping factor and other parameters. So the further analysis was undertaken by Transgrid, which showed that with appropriate tuning and potentially just simply a higher MVA capacity of the battery, you could see a response from the battery that was closer to what you see from synchronous machines. But as noted previously, there were some restrictions in the generator performance standards as to how the battery was expected to operate, which meant that that kind of tuning couldn't be done for the Wargrove BESS. The other thing to caveat is that when you do undergo that process of tuning the battery to maximize the inertial response, there are consequences for damping and broader grid stability that need to be worked through and weighed up. The last thing I'll note is that there were some examples where the inertial response of the battery to disturbances was outside what had been originally expected from the battery, and there's some discussion in the papers as to why that may have been the case. One key note that came from the roundtable discussion was the need to particularly look at the response of grid forming batteries to combined events where there's both a frequency and a voltage disturbance at the same time, rather than just focusing on the response to frequency deviations. So that's definitely an area for further investigation. So to summarise the key findings on this particular point in terms of inertia from BESS versus from synchronous machines, one of the key findings was actually that the response varies depending on the manufacturer, and that's what part of the difficulty that was flagged by Transgrid in the Wargrove BESS reports in evaluating the response of grid forming batteries in comparison to synchronous machines. Some of the nature of the response is due to the particular implementation of that particular OEM. So we know that there are OEMs out there where the inertial response doesn't change depending on the magnitude of the event that triggers the response, whereas some OEMs, the type of inertia response, effectively the inertia constant, will be different depending on the magnitude of the event that triggers the response. But that's just one aspect of the way in which the implementation of this feature differs across OEMs. The other key thing to note is the headroom constraints. So if a BESS is discharging at its maximum capacity, for example, it can't provide an inertial response, or the inertial response that it can provide is very limited in the same direction as it's already discharging. So this is in contrast to synchronous machines, where they can provide an inertial response regardless of the active power output, because it's about the stored energy in the rotating mass. So that particular aspect means that there's some specific considerations needed when you're procuring inertia services from a grid forming battery that you don't need to think about if you're procuring it from synchronous machines. So with all those caveats though in mind, sorry, actually, before I go on, one last thing to note is it's a sort of stepping back perspective. The fact that the volt current provided by grid forming inverters, there's a limit in the current output at 1.2 to 1.3 per unit output, means that in general the inertial response that can be provided from the equivalent MVA of inverters versus the equivalent MVA of synchronous machines may not necessarily be the same. And may be lower for grid forming batteries. You might require a larger volume of MVA capacity from batteries to get the same response that you can get from synchronous machines. But with that caveat in mind, that there definitely is examples of the inertia capability being demonstrated by the projects that we observed. And one point worth noting from the Hornsdale market report was that the inertial response that the Hornsdale project is providing is actually contributing to broader system stability and giving more time for the wide area protection scheme from Electronet to come into effect, which reduces the likelihood of interconnected trips on the Hayward interconnector. That's just one specific example where already the inertia being provided by these projects is actually having an effect to improve grid stability. Okay, so now just turning to system strength. The first thing to note is that there's slightly less operational examples of the system strength capability provision from these two projects, as they came online slightly later than Wargrove and Hornsdale. But there nevertheless is a lot of knowledge sharing that has taken place showing the service that is being provided by these batteries. So Darlington Point and Broken Hill BESS were both providing voltage support to the network at weaker areas of the grid. The Broken Hill battery system modelling report provides a lot of great detail on the modelling that AGL and their partners undertook to demonstrate the effect that the BESS was having. And what can be clearly seen is that there are voltage oscillations on the network that are occurring that once the Broken Hill BESS connects to the network, those voltage oscillations reduce within the high-frequency real-time digital simulations that were being undertaken. So that shows the impact of the BESS on the network. And similarly, there are examples that the Darlington Point battery have reported on where there were voltage disturbances and the battery was shown to be providing a very fast reactive power response to those disturbances. So the example I wanted to call out, though, is an interesting event that occurred when the islanding of the Broken Hill area of the network took place. And what this demonstrates is it's not directly what the battery was designed to demonstrate, but it does indirectly show one of the key capabilities of these grid forming batteries, which is the ability to operate in low SCR points of the network. So after the islanding event occurred, the BESS went offline as it was required to do under the current its current generated performance standards. But then in discussion with AMO and Transgrid, the BESS was brought back online to provide some support to the gas generators. And it was just simply operating in a fixed charge discharge mode at the time. But what's notable there is that a grid following BESS in the same location very likely wouldn't have been able to connect because of the low SCR at the time. So that's just one example where that illustrates the specific capability that's inherent within grid forming batteries to operate in those low SCR conditions. The other finding that did come out of the Darlington Point and Broken Hill projects was that additional capacity has been unlocked on the network to bring online renewable generation because of these projects and their contribution to system strength. So there was wide area network studies that were carried out by some wide area networks modelling that was carried out by Broken Hill, the Broken Hill BESS project. And it found that particularly when the BESS was providing its maximum reactive power output, an additional approximately 40 megawatts of renewable generation in that area could come online because of the ability for the existing static var compensators to regulate the grid voltage because of the additional voltage support that the BESS was providing. And similarly, for Darlington Point, the recent findings from Transgrid's analysis of the effect of that service provided by Darlington Point is that an additional 120 megawatts of capacity can be used on the particular line that the Darlington Point BESS is supporting. So it's providing fast active voltage control services, which reduces the voltage instability on that line and ensures that it doesn't go outside the bounds of the line. And so, yeah, these are two examples that have been found through these projects where the bringing online grid forming batteries has enabled more renewable generation to be online. So I'll now hand over to Caitlin to discuss the more commercial considerations that we looked at in the report.
Excellent. Thanks, Josiah. So firstly, looking at the system level before we go into nitty-gritty project level, what we did find was that we don't actually require all projects to be grid forming to unlock the system benefits. In fact, AEMO commissioned a report last year that sort of indicatively found that even 10% of projects in grid forming does deliver a system benefit. That said, there are sort of project level incentives that exist, and they're sort of driving the number of projects that are electing to be grid forming to be higher than that 10% number currently. So, for example, the system strength impact assessment guidelines or framework that exists at the moment does encourage projects, whether it's a battery project or a hybrid project, to opt for grid forming technology and self-remediate their system strength. And for example, Transgrid have noted that in their current pipeline of connection applications, that around 60% of battery projects are already doing this. That's not necessarily a neutral optimal outcome, and we'll touch on that in our next paper. So while the technology is software based, there are sort of CapEx implications around oversizing to meet certain system strength obligations or GPS performance conditions that impact the overall business case for the project in grid forming versus grid following and in the network characteristics of that project location. So also thinking about sort of the contracting complexity that exists in BESS projects, regardless of grid following or grid forming, there's sort of warranty constraints around cycling that need to be considered, and then adding extra layers of network support services agreements does add kind of layers of contractual requirements on what's already a complex setup. So it's complex, but it's definitely doable. And Darlington Point showed that they could procure via RIT response with Transgrid those fast-acting voltage support services to Transgrid. That sits alongside a long-term tolling agreement with Energy Australia for full operational control of the battery and able to kind of value stack those two network services as well as the market revenue side by side. And similarly, Wargrove had another layer of complexity, being a TNSP-owned asset that they were required to ring fence and have Iberdrola operating and trading the battery as well. And so under that circumstance, only around 5% of the energy storage capacity was required to be explicitly reserved for inertia and fast frequency response. So it's not necessarily a huge impost on the trade-offs of, okay, we need to reserve a certain portion for being able to provide inertia and frequency response while still allowing Iberdrola to trade a lot of the time and kind of maximise the typical energy arbitrage and FCAS market participation. And sort of not only complex, but also quite complementary, which is interesting. For example, the Wargrove example noted that at around three-quarters of the time, there was sufficient sort of, the BESS was either idle or not charging at full ends of their charge-discharge capacity, such that it could provide fast frequency response and inertia alongside the typical commercial trading operations. So they are sort of complementary in nature. And similarly, Darlington Point, you can see here, this is just from their first 6 months of operations. It's quite a typical profile, and as I mentioned, it had no discernible impact on their ability to provide the voltage control services to Transgrid, while also having Energy Australia able to charge and discharge and do what they wanted to do under their tolling agreement. So on the basic side, that seems to work. I think inertia is sort of an ongoing discussion in the Australian market at the moment. There is no inertia market currently, and the AEMC released their draft determination last month that they're not proposing to introduce an inertia market. As such, the kind of current BAU remains where projects will be required to contract bilaterally with an NSP via kind of a network support services agreement for to be able to realise the commercial value of the inertia service provided. That said, there is again another layer of kind of complementary nature where that inertia may only be needed in sort of a credible contingency event scenario, in which case the battery would be enabled by AMO and providing that service, and then in kind of typical times it's trading and participating in FCAS and energy market arbitrage. So it's sort of a complementary nature of the type of system events that require inertia versus typical operations. Probably another interesting rationale of why grid firming technology is helpful is that it does have sophisticated kind of software behind it that can enable the operating protocols to be configured such that all these layers of contracts and contracting requirements can be configured into their trading and dispatch algorithms, and such that you aren't running into potential non-compliance. Kind of penalty for non-compliance is definitely going to hit the bottom line of any project. So keeping that in consideration in operations as well, and ensuring that none of the kind of contractual arrangements are being breached. And finally, probably an interesting point to close on the commercial considerations is that there is a natural trade-off that exists between the active power set point headroom and the inertial response, particularly when the inertia isn't particularly valued outside of a network services agreement. So the more headroom that is available, the greater the inertia response, but that obviously impacts your ability to do other things with the battery. So there's sort of a trade-off that needs to be weighed up for any project in terms of how much headroom is being reserved for inertial response and how that's being sort of contracted and valued in that contracting structure. I'll pass back to Josiah for kind of a wrap up and next steps.
Caitlin. So noting the time, I'll just briefly cover some of the key findings. The overarching perspectives that came out of the discussions with proponents and the roundtable were that at present, a lot of the discussion around grid forming technology is looking quite specifically at how in the coming few years, as we are seeing the retirement of thermal generators, we can replace some of those services with grid forming batteries, similar services being provided by grid forming batteries. But what's really needed is a longer term perspective of what is the grid going to look like in 10 years time, when you have a very, very high level of inverter-based resource penetration and a much larger volume of grid forming batteries online. And so looking forward to that future state of the network can help inform what kind of decisions we make now about the restrictions and implementation of grid forming technology for projects that are connecting right now. And similarly, a similar point was a need to focus on the actual outcomes that we're seeking, rather than just the inputs. So the inputs being the inertia services, the system strength services, the particular voltage support services that the grid forming batteries can provide. But it's important not to lose focus on what are we actually trying to achieve through those services, which is ultimately voltage and frequency stability. And there are different ways of meeting those outcomes, rather than just like substitution of capability from one technology to another. And yeah, as has been noted in I think it's the inertia requirements methodology published by AEMO, as you have more fast frequency response from grid forming batteries, the amount of inertia that's needed on the network actually reduces. Just a quick note that several of the recommendations that we've published are very much in line with ongoing work streams that are already underway with AEMO, led by AEMO, and also being undertaken in the knowledge sharing that's happening on the future projects that ARENA's funding for grid forming batteries. So some of the key technical findings, the principal one really was that standardization will benefit the industry and the adoption of the technology, as there's more standardization and agreement on how the grid forming response is defined and consistency across OEMs. The regulatory requirements and the contractual frameworks will be able to better accommodate that technology. There is a need for an improved understanding of the inertial response from grid forming batteries, particularly the headroom constraints and the trade-off between higher inertia and not creating voltage instability, which was observed particularly in weak grid areas. And lastly, as a general point, the need for further studies, particularly wide area network studies, and also different kinds of studies, particularly small signal studies, to better understand how the network is going to be responding when there's a greater number of these technologies all online and operating at the same time. And then on the regulatory and commercial side, the biggest finding on the regulatory side was, as discussed, that there were certain clauses of the GPS that likely needed an update to better account for the GFM technology. And as noted, these reforms are underway. The need for collaboration through the commissioning process is paramount. And then a final point that was discussed, and we go into further detail on it in the paper, is the potential inherent within grid forming batteries to tune the parameters such that the response matches what the grid requires at that particular point in time. There's a lot of potential capability there for batteries that you can tune the response as the network changes and evolves over time, which you can't do for synchronous machines. But there's obviously a lot of implications that has for the way that we approach the connection process, and also how the commercial case for batteries looks over the lifetime of the asset. So there's a more detailed discussion of that in the paper, which I'd encourage you to check out. And lastly, on the commercial point, as the technology and the industry matures, the uncertainty associated with the projects is likely to reduce over time. And then the final point on that Caitlin really spoke to in detail, the way that system support services are procured will need to take into account the unique way in which grid forming batteries provide these services and the value stack that's required alongside the other market participation that they do. So that about wraps up the findings from this paper. As noted, there is a forthcoming one in the coming weeks, looking at the next set of projects. Yeah, with that, I'll wrap up, and we can go to some Q&A.
Beautiful. Thank you very much, Josiah and Caitlin. That was a great overview of the report. Just a reminder to everyone that the report's up on the Knowledge Bank at the moment. So there's a link in the chat which you can go and read through in more detail. I'll also note that this isn't the last report coming in this series. We have another one that's coming up and probably published around August. So stay tuned for that. I think we've got a couple of minutes left for a few questions to our panel. So we've got Lyndon also joining alongside Josiah and Caitlin, and we've got Ashley and Paul as well from Ekistica. So jump into the Q&A box, pop your questions in there. We probably won't have time to answer all of them, but if we don't get to your question, we'll send you back a response from the team at Ekistica and ARENA. So with that, we might kick off with a question from Max Rurath, who asks around Transgrid System Strength Project Assessment Conclusions Report, or PACR. and has asked around what evidence there can be to provide to demonstrate that grid forming technology can contribute to minimum fault level requirements. Now, noting that wasn't exactly the scope of what we've discussed here, but interested to see, if you guys have any perspectives on that from some of the data you've analysed through the portfolio so far.
Yeah, I'll provide a brief response and then pass to colleagues to weigh in. But the focus of these projects was on efficient levels of system strength, so the contribution to voltage waveform stability rather than the contribution to the minimum fault level. We do explicitly note in the report the fact that that is one aspect of system strength that at present there is not the recognition that grid forming batteries can contribute to this, or there's some uncertainty around the ability of grid forming batteries to contribute to this. I'm not sure if Lyndon, if you had any further perspective on the works underway on that particular point.
Yeah, look, I think it's an area that there is considerable discussion underway, both within Transgrid, but also other associated entities, including AMO and some of the other NSPs. I think the challenge that exists for all of the NSPs in considering these options at the moment is it's a trade-off between what is known and what is potential relative to the timeframes for implementation. And so the needs and demands for fault current and synchronous fault current in the network are well understood and are needed now. The potential opportunity, and I think the work that is coming out of these reports and others like it, highlight the value of what could be provided by grid forming batteries. However, I don't think it is necessarily yet the case that there is enough data to be able to say definitively that these capabilities only need to be provided by grid forming batteries. I think there is an open discussion and continues to be an open discussion around the longevity of batteries. I think we are, and I'm sure many of you would have seen that batteries are regularly being closed with long-term service agreements with defined availability and reliability agreements for a 20-year term. How that plays out in sort of beyond the immediate process of commissioning, and whether or not those batteries are able to provide those functions in accordance with the limitations of those guarantees, and therefore the extent to which long-term investments can be made around those. I think that is still an area that is being assessed. And in that context, while I'm not necessarily saying I agree or disagree with the conclusions of the Transgrid's preliminary assessment, I can understand collectively the nervousness around ensuring that we don't put all of our eggs in one basket. The practical reality is if you dive in and assume that you're going to do everything with grid forming batteries and then work out that it doesn't work, the timeframes for rectifying that circumstance with jumping into sync-ons are really significant. So I think we move into a realm where it's not just about whether technically something can be done, but strategically and practically, how do you manage this in a changing system? And I think some of the comments that Caitlin was making around the commercial frameworks around these also have to be resolved. And I think from an engineering perspective, one of the things that we all need to be very cognizant of is that just proving that something is technically capable is really important, but in and of itself is not sufficient to justify change unless we can demonstrate that the aggregate risk profile of change to a world where we rely solely on grid forming batteries is appropriate.
Fantastic. All right, that's a great response. Thank you, guys. I think we've probably just got time for one last question, and it's a biggie. We'll go out on a good note. Farhan's asked, what is the optimal mix of grid forming versus grid following inverters for system-wide stability, and how do locational signals play a role in guiding deployment of that?
I might take this one if I can, Josiah. Look, it is a fantastic question. I'd probably preface it by saying that anyone who asserts they know exactly what that number is should probably be ignored, because there is yet to be enough work to really prove what that mix should be. All of the information and analysis that I've seen to date strongly suggests that it would be inappropriate to assume that the best solution is to make all batteries grid forming. We can actually see that in having areas where there's too many grid forming batteries, particularly if they're really not being optimized properly, that will actually create other issues, and particularly in intermodal oscillatory issues. Clearly, everything being grid following is also not going to be optimal, because it creates all the issues that we're trying to actually solve right at the moment. I think the question for me is actually not so much what is the optimal size between grid forming and grid following in a sort of an abstract sense of, is it 10% or 15% or 20%? But I think it's going to be a question of what is the optimal sizing of grid forming utility scale batteries in the context of rapid uptake of behind the meter or sub 5 megawatt scale grid following batteries that we're likely to see throughout the rest of the network. And so if we imagine that behind the meter batteries or behind the meter storage follow even half the growth rate that behind the meter PVs had over the last 10 years, then the assumption around what portion of the utility scale battery should be grid forming will be different than if behind the meter storage doesn't get taken up at the same level. So I think it is an area that as an industry we need to be very mindful of. We need to be mindful that anytime we discuss utility scale assets, we have to be cognizant that they are being integrated into a dynamic system where what is occurring behind the meter is changing rapidly and will change the dynamics of the system that we need to manage. And so I think then that starts to raise questions around whether or not networks, and particularly DNSPs, start to form views around the level of grid forming that they need in portions of their network, where there is a greater stability requirement for that, compared to what might be occurring more broadly in other network in more remote or disparate parts of the network. I think it will be, whatever that answer is, I think it will be heavily influenced by the different jurisdictions and different regions. And I think it'll be heavily influenced by the nature of the generation infrastructure within that region as well. That is a very long way of saying I don't know, and we'll find out in the future.
All right, I love it. And that's a good takeaway as well. If you claim to have the answer, you don't. Thank you very much, all of the Ekistica team, for joining us and providing a really great summary presentation. And yeah, really encourage everyone to go and have a read of the full report on the ARENA Knowledge Bank. Just before we go as well, it's everybody's favorite part of a webinar. We have a QR code that will be up on the screen. If you can quickly scan that and provide us with some feedback on this session and what you'd like to see more of or less of, so that we can tune this going forward, that would be fantastic. But thank you again, everyone, for joining, and hope you have a great rest of your morning or afternoon.
Yeah, thank you all. And stay tuned for the next report that we're publishing next month with the updates on the new grid forming battery projects.